In this paper, we review the important recent results of buoyancy-driven turbulence. Such flows come in two forms: stably stratified system, that is stable, and convective turbulence, that is unstable. These two systems have very different behavior because of stability, and their scaling are also different. First, we consider quasi-isotropic stably stratified turbulence. For such flows, the kinetic energy is converted to potential energy and then to dissipation. This is due to the stable nature of the flow. Hence, the kinetic energy flux decreases with k, and it shows k minus 4 by 5 power law. The kinetic energy spectrum shows minus 11 by 5 power law, which is evident from the DNS result that compensated kinetic energy spectrum is flat. Thus, the stably stratified flows have very different phenomenology as Kolmogorov spectrum. Turbulence in RBC has very different phenomenology than stably stratified turbulence. This is because the temperature feeds the kinetic energy, hence the kinetic energy flux does not decrease with k, and we observe constant Ke flux, This is seen in high resolution DNS for very high Rayleigh number. Here the Ke flux is flat for considerable wave number band. Now, constant Ke kinetic energy flux leads to Kolmogorov spectrum K minus 5/3, similar to 3D hydrodynamic turbulence, and we get a pretty high large range of 5/3 power law. The shell to shell energy transfer is local and forward. The ring spectrum is nearly isotropic, thus Rayleigh-Bénard convection has similar turbulence behavior as 3D hydroturbulence. The RMS value of RBC terms show interesting features. For example, the viscous term and buoyancy term nearly balance each other. Hence, acceleration is essentially provided by the pressure gradient. Again, similar to hydro 3D turbulence. Spectrum of thermal fluctuation exhibits bispectrum. The upper branch is K minus 2, which is because of the walls. And the lower branch corresponds to other modes. So, the main results discussed in the paper are quasi-isotropic stably stratified turbulence yields Bolzano-Bokov scaling K minus 11 by 5, and turbulent RBC for PR approximately 1 yields behavior similar to 3D hydroturbulence, which is minus 5/3.